Hi everyone, welcome to my channel. In this video I'm going to breadboard a simple circuit and we'll do some basic circuit analysis. I have a video where I did some simple breadboarding, but I think the Arduino was a distraction. I only was using the 5-volt regulator from the Arduino as a power source for the circuit. But in this case I just have a breadboard. This is a large breadboard. Solderless breadboard. It just has these contacts that grab onto leads when you push them into these holes. And I've got a 9-volt battery as a power source with this 9-volt battery connector. So this just snaps on. So you don't need anything fancy like a power supply. You could just use this or some AA batteries. And I've got some components here, some LEDs, some resistors, potentiometer, and some jumper wires. So we'll use some of those. So to start off with, I'm just going to connect these leads here from the 9-volt battery. So we'll use these side columns here. This left will be the positive, and all the way down this right side column here with the blue line, this will be our negative. Let's get a closer look at that. And if you recall on the breadboard, on these side columns here, these are all connected all the way down this line, designated by the blue line here on this particular breadboard. We'll use that as the negative, and these two pins or two holes are not connected, so they're isolated from each other. And all the way down here, we will have access to the positive. So this is the positive side, and the blue will be the negative. And we could just take a component, plug it into any of these holes to get access to the negative and to the positive, and put the other side, or we can put the components here and then jump over with a wire to bring over our positive or negative. So we'll start off with a 220 ohm resistor. So I'll just plug this 220 ohm resistor in to the breadboard, like so. You can see what's connected here and here. And I'll add a jumper wire. I could just have put this side into the positive, but I'm going to use a separate wire. And on this side, all these are connected. So you just plug into one of the holes right next to the lead of the resistor, and then plug that into the, I want that going to the positive side of the plus 9 volts, like so. And then next I want the LED. So I've got an LED here, a green one, and it has a flat side here. If you look at it on the left, it's a little flat. That's the negative side, and the longer, it's the shorter lead, and the longer lead is the positive. I want the longer lead going toward the plus 9 volts. So I'll put that next to that other side of the resistor and press that into the board. And I'm just going to take a jumper wire. Let's back off here a little bit and connect to the opposite side of the LED. And I can use this wire as my on-off switch. So when I go to touch the negative side here, this negative row that we've got the negative side of the battery connected to, we'll turn on this LED. It will complete the circuit. And there we go. a little circuit there that turns, you can turn an LED on and off. And again, that's a 220 ohm resistor connected to the positive of the 9-volt battery right here. And the other side is connected to the LED, and then the LED is connected to ground, to the minus side of the battery. So if we want, we can also connect a switch that's normally off, and when you press it, it makes a short circuit and completes the circuit and connects the other side of the negative side of the LED to the negative side of the battery. When you press it, put that into the circuit here, and the other side again, I can just keep that plugged in because I'm going to use the switch now to turn the LED on and off. So when I press this, LED goes on. So let's draw this circuit out and do some circuit analysis. So if we draw the schematic for this, we have the symbol for a battery. And in this case, we have a 9-volt battery. That's plus, and this is minus. And we have a 220 ohm resistor. And we have an LED connected where this is the anode, and the line here is the cathode. And then we have a switch that we've installed. And then the other side of the switch goes to the negative side of the battery. And that's the circuit. So let's do some analysis on this circuit. Let's first see if we can figure out how much current is flowing through this circuit. This is a series circuit, meaning that the current that flows through this is going to be the same through each component because each component is connected in series. When you close this switch, the current through this switch will be the same as the current through this diode, which is the same as the current through this resistor. And the current we label as I. And one of the first laws you learn about in electronics is Ohm's law, which states that resistance is equal to the voltage divided by the current. The voltage across the resistor divided by the current through the resistor. And if we manipulate this formula, we can come up with a formula that will tell us what the current will be through this circuit. And that will be I is equal to the voltage across this resistor divided by the resistance value of the resistor. And if we know the value of the current through the resistor, we then know the value of the current through the diode and through the switch, because it'll be the same. There's no other path for it to go. The current has to go through the resistor, the diode, and the switch. It's the same amount of current from the positive to the negative of the battery. So let's measure the voltage across the 220 ohm resistor and then calculate the current. And then we can use a meter in series with this circuit to measure the current to see if the real current value equals the current value that we calculated with this formula. So I'll connect the meter across the 220 ohm resistor, like so. Let's put this right here out of the way. And let me press this button, and we'll measure the voltage across that resistor. So we measure 6.24 volts, 6.23 volts, it's dropping a little bit because this battery can't continuously maintain the voltage or the current through this circuit. So we'll call it 6.24 volts. So let's calculate the current. So we have 6.24 volts divided by 220 ohms. Got my calculator. I've got 6.24 divided by 220 ohms equals to 28.36 milliamps. So this is equal to 28.36 milliamps. Milliamps are units that are smaller than amps. It's 10 to the minus 3 amps. So now let's go measure the current, the actual current through the circuit with a meter and see if it's close to this 28.36 milliamps that we calculated. Now when you measure current with a meter, the meter has to be in series with the circuit. The current has to flow through the meter, so we have to break the circuit at some place. I'll break it here. I'll remove this wire, or lift one end of the wire up. That's connected to the resistor, and one lead of the meter will go to that side, and the other side, the other meter connection will go to the resistor. So the current will have to flow through the meter on the right to be able to get to the resistor. So this meter is measuring current, and the meter on the left is measuring the voltage across the resistor. So let me press this button, and this should measure somewhere around 28 milliamps. Let's see if it does. And there we go. We have 28.3 milliamps. So that's close to what we calculated. So that verifies that Ohm's law does work. If we know the voltage across a known resistor, we can calculate the current. Now another basic rule in electronics in this series circuit is that the sum of the voltages across each component, if you add them together, they should equal the total voltage, in this case the 9 volts that we have across the whole circuit. So we know we've already measured the voltage across this resistor as 6.2 volts. We can measure it again. And we press this button, and we have 6.24 volts. So if we have 9 volts, and we subtract 6.24 volts, we should have around 2.76 volts across the LED when it is on. There should be negligible voltage across this switch because it's essentially a short circuit when we press this button. So if we measure the voltage across this LED when we close this switch, it should be somewhere around 2.76 volts. So we have 2.36 volts, which is a little off, but it might be that we do have a little bit of a voltage across this switch, or it could be that this is not maintaining 9 volts, because it is only a 9-volt battery, and it's hard for it to maintain around 28 milliamps without dropping the voltage across it. So the switch again has really no voltage across it when it is closed. It's essentially a short circuit. So if we measure, let's see what the battery's doing. If the battery is still able to maintain its 9 volts when we turn on the LED, that might be a problem. So if we measure this side of the switch, clip on right there, and this side here of the resistor, see, we only have 8.81 volts. We do not have 9 volts. This battery, the voltage is dropping because we're drawing too much current from this battery. So if we press this button, we'll see if this 8.8 volts even dips a little bit more. And you can see it does. It dips down to 8.6. So that's sort of like when your car battery starts to die and it can't turn over your motor. And it's because you've drained the battery so much that it doesn't have enough voltage or enough amp hours left in it to turn over your motor. So that accounts for the little bit of a discrepancy there. So again, we're measuring 8.8 volts. Let's write this down. We actually have, instead of 9 volts, we have 8.8. But even when we turn the LED on, it dips down to 8.6. So the voltage across the resistor, again, is 6.24 volts, around 6.24 volts. And the voltage across the LED is 2.37. So 2.37 plus 6.24 equals to 8.61 volts. And we have 8.6 volts measured across the 9-volt battery when it's drawing current through the circuit. So the voltage across this battery is slowly dipping because we're drawing too much current out of it. It's not going to last forever. So even with this simple series circuit, we were able to use Ohm's law to show that there was a discrepancy between theory and reality. And in theory, we had a perfect 9-volt source that did not dip down when we drew current from it. But in reality, the 9 volts dropped down to 8.8 volts and dropped down to 8.6 volts when we turned on the LED and drew current from the battery. And by actually comparing the physical measurements with the theoretical measurements, we saw that we needed to account for the loss in voltage because the theory states that the sum of the voltages across these components needs to equal the total voltage being supplied. So we knew we were losing voltage somewhere, and in this case, again, the 9 volts was not exactly 9 volts. It would dip down to 8.6. So that's a simple circuit, and you can see some of the complexities even with just a few components. And we used Ohm's law to calculate the current through this circuit, just knowing the voltage across the resistor and its resistor value. And we showed that using Ohm's law, we were able to figure out why there was a difference between what we calculated and what we found in reality. So I hope you learned something from this video. Please subscribe and or comment or thumbs up. And thanks for watching.